Hi, in this video, we want to take a look at basic image classification in keras. All right, and we're going to be doing it with R. All right, so something I really like about keras with R is that it is easy peasy lemon squeezy to get this going on an R system. Super easy compared to Python. So if you want to jump in, start doing some TensorFlow stuff, start working with keras, R is the fastest way to get into it. Right now, this example is modified from TensorFlow to rstudio.com. If you want to get into the original text and their comments and everything, please dig into it. All right, so I want to work through this example. And so the first thing I'm going to do, I'm going to go ahead and change some options. I'm going to make it so that digits only print out the three digits, and then scientific notation, or the system is more prone to giving us the full floating version, the regular version of the number, rather than scientific notation. That's what the SciPen parameter does. All right, so first thing I need to do, need to get my data. All right, so what I'm going to do, I'm going to get the fashion MNIST data set from keras. All right, so something that's interesting about the keras package in R is that we don't actually use the data function to get our data. We use a dedicated function. Notice that this is a function to get the original data set. Okay, and now I'm going to go ahead and call that list underscore fashion. Now, this data set is coming to us as a list where we have training set, test set, we have predictor variables called X, and we have target variable called Y. All right, so we have we have a list going on. So now there's more to it than that. If I take a look at this, I start looking at it, the X's are actually 28 by 28 grids. So each observation corresponds to a 28 by 28 grid. Well, why is that? Because we're doing image classification. So here we only have a 28 by 28 grid of values for the actual picture. Actually, I'll scroll down to show you what it looks like. We'll get through all this in a moment, but here is an image coming from the data set. And so, we can see it's very coarse, but for the purpose of learning basic image classification, this is a good place to start. And so we can see that we've got darker and lighter values. Okay. So what's going on is that each individual point has a number between 0 and 255, which corresponds to lightness or darkness, and everything's on a gray scale, just so that we're starting out on this image classification scheme. And so one thing I want to do, just as a personal quirk of mine, I don't like having somebody give me the test set. I don't like someone giving me the training set. I like to grab all of it. I want to work with it, the whole set, and I want to choose how my data gets split up. So what I do, I go ahead and I take the training predictor variables and the test predictor variables, and I put them together into one larger data set. Now, each observation is a 28 by 28 grid of values. All right, so this ends up being a three-dimensional array. So the first observation is 28 by 28. The second observation is 28 by 28. The third observation is 28 by 28. And so all in all, I'm going to have 70,000 observations and 28 rows, 28 columns in that manner. All right, so this is not a data frame. This is an array. Okay. So here, the array bind package, I'm using the namesake array bind function, and I'm saying go along the first dimension to stack these on top of each other. Okay, so now the next step, and this is a step that gets missed a lot when you're going through like help documentation and you're going through tutorials and videos and blogs about neural networks, is that neural networks, a lot of them prefer to have the data between 0 and 1. All right, as the data comes to me, it's between 0 and 255. Okay, so what I need to do to rescale that, I just divide by 255, and that makes sure that everything is going from 0 to 1. Okay, this is an important point. If you don't do this, a lot of your neural networks will fail. Right now, I want to get all my target variable values together. And so you'll notice I've got train, then test. I have train, then test. It's in the same order. All right, so now here are the actual values of the items that we have. So we see that we have 10 different items, and our goal is to classify the image of each item into one of these 10. Okay, and do it as accurately as possible. Now, if I look at the actual data coming from the Y portion, that from our target variable that's in the data set, everything is digits going from 0 to 9. All right, so here, this step just names this vector 0 to 9 to make sure I have the correct correspondence. Starting at 0, ending at 9. And so the V target is just, what I'm doing here is I'm getting the categorical representation instead of the integer representation of our target variable. And so when I do table on that, I can see that we have an even split of everything. So everything is at 7,000. So what this does for us as we're working on our initial model is that we don't have like an over favoring or under favoring of anything. It's all pretty even throughout. It's perfectly even. A problem can arise in a classification problem if I have one like category that's very, very small in representation, then it doesn't get much of a representation in the data. So, and if it doesn't get represented in the data, it's not represented in the model. Remember, our models always look like our training data. Our models always look like the data we build them on. Therefore, if I had, let's say, one of these that only had 100, which would be very proportionally small compared to the others, if there's only 100, then trousers wouldn't get really a full representation in the model. All right, here's the dimension of our predictor variables. So we can see that we have 70,000 observations, and each observation is a 28 by 28 picture. Okay, and we have 70,000 target variables also. So now, what does each observation look like? Well, what I'm going to do, I'm just grabbing the first one. I'm taking the first observation, I'm taking all the rows and columns corresponding, and then I'm just printing out the values just so we can see what's going on. And we can see that we have a lot of zeros. So whenever I have a 0, that means that there's no portion of the object in the image. When I see something going on here, I know that this is a very, like a very dark region of the picture. So looking at this, I can't tell what is this image. It's just a bunch of numbers. Maybe you can read it. I can't. Let's go ahead and see if we can visualize the image. All right, so something that's important to understand about this type of problem is that whenever I work with it, I actually work with a data frame. Data frames are two-dimensional. I have rows, I have columns. Here I'm working with data that's three-dimensional. The only way that I can work with this, the only way that I can get a visualization of this image, or excuse me, the only way I can get this image into the neural network is if I convert it over. So in this process, I'm going to convert this over to a data frame, and I'm going to pass that data frame to ggplot. All right, so I just take the first item, which is an ankle boot, and then I convert it to convert some numbers for the column names. And here, what we're doing, the critical step is this gather function. All right, so you saw I have a grid. What this is going to do, this is going to take the rows and columns that I have and then put it into a long format. And this is the format that ggplot likes. And so now, in this format, after I run the tidyr packages function gather, here is your data I'm passing in. The key is just the column label, and the value is a column label. And this is saying don't mess with the y coordinate. All right, so we can see, for 23, 28, this is level of darkness. 24, 28, that is darkness is 0, and so on. So now let's go ahead and plot it. I'm just using the ggplot package. So I'm just going to use a geom tile. I'm going to use scale fill gradient. All right, so what's going on here? Low values correspond to white, high values correspond to black. NA values are in A. We are reversing the Y scale because of how matrices always have in the upper left-hand corner is the 1, 1, and then the lower right-hand corner is the largest, like in the largest one. And so that's reversed from how we want it in the vertical direction. So I have to reverse it. Theme minimal just says, like, don't print a whole bunch of stuff. Whereas this is basically just blanking stuff out. The aspect ratio makes sure that it looks like the image, not the plot. So remember, when I plot something in R, it usually has like certain dimensions that's not perfectly 1-to-1 in the ratio of X to Y axis. And so this forces it to have aspect ratio of 1. And there is our ankle boot. Okay. I mean, I really can't tell what I'm looking at, but that looks like an ankle boot to me. Here are the toes, here's the ankle part, here's the heel. Good, good, good. All right, so now we can run through this, and here, this is using base R to accomplish this. This is literally copied and pasted from the website, is that we can go through and we can actually take a look at each of these just to get a feel for what our images look like. And so the critical aspect of this to keep in mind is that I'm taking the image, which corresponds to one observation, and then I'm going along the columns and reversing the order. And then I'm plotting the X and Y values. So here is just taking, X row, or taking 28 rows, 28 columns directly off of it. I didn't have to reshape the data. Oh, and the par MF call equals 5, 5. That specifies that we have this 5x5 grid of images. All right, so now next thing I want to do, I want to define the image structure for my actual keras model. All right, so I'm going to use piping. Piping is this operator. This is the slick, sexy, fancy way of doing R currently. Now, the McGritter package is needed for this. This is where the operator is like stored. The piping makes a lot of code easier to read, but also it does slow things down. Here, it's not really an issue, but that's something just to kind of keep in your mind, that it's faster to just manually type in things. What the piping operator does, it takes the previous item and passes it to the first position that's undefined in the function. All right, so we're going to build a sequential model in the keras package. Now, this layer flatten, what I'm doing is I'm taking those 28 by 28 grid for each observation, and I'm converting that into a data frame. Now, next one is, this is where I start kicking off my actual neural network. I'm saying I'm going to have 128 units in here. And for my activation function, this is RelU. RelU is a constant and linear function, piecewise defined, that is used to basically mute aspects of the data, let other parts of the data speak for themselves. Now, this layer dense operator, what this is doing, this is taking 10 nodes, and this puts a node for each category that we have. Okay, why is it doing this? Because we're trying to set it up so that each node is trying to figure out, is it this on a shirt? This node figures out, is this a shirt? This node figures out, is this a ankle, ankle boot? Is this a pullover? So we have 10 different categories, 10 different nodes, and they're going to correspond in this example. Now, our activation has to be one that can handle categorical data. If I don't do this, if I don't have the soft max, It's going to look at those zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, those numbers, and try to fit it in terms of more of a numeric presentation rather than working with categorical data. Now, this next part, this compile, tells keras how to actually implement. So we're going to optimize using the Atom protocol, and we're going to be working with entropy because we're working with categorical data. And I'm telling it to work on the accuracy. The accuracy is the part that we want to focus on. Now, something I want you to notice is that at no point did I put data into this. This is only the shape and the structure of the model. This is not the actual fitted model yet. We have not worked out our parameter values. And so here we can see that we have, over 100,000 parameters. And here we have 1290 parameters. You'll notice that this is 128 plus 1 times 10. And so we have a lot of parameters. In fact, we have more parameters than we have data. All right, so remember, anytime you do something like that, you are prone to overfitting. So in real life, I would want to go get more data before I would be fitting this particular model structure. All right, now I'm going to fit our model to the data. Now, what I'm going to do, I'm going to pass the model structure that I've already established. I'm going to use a fit function from keras. I'm going to give the training function, or the training data, the target variable, tell it how many iterations to go through, and I'm going to do a validation split. Okay, so what this is going to do, it's going to go up, it's going to split the data in two, it's going to fit the model on this data, and then it's going to check the accuracy on this data. And so this way I get an estimate of how well my data will perform. This is called the training set, is what we build the model on. The validation set is the data that we use to validate the model on. And so now I can plot it. All right, the loss function is the function that is used to evaluate or used to guide the iterations and the improvements as it goes through the different iterations. So we can see that we start out, the training loss goes down, and it probably would keep on going before it got completely flat. But we notice that the validation goes a little bit up here. So this is a sign that maybe I'm starting to overfit. Now here, my accuracy does something similar. It's going up, and then it starts going downward. Okay, so it probably would flatten out, do a little bit of bumpiness, but I don't really know without doing more iterations. There really is not that much of a difference between these two values, vertically speaking, so it's not a big deal. All right, so now on my final model, I want to use all my training data. I don't want to leave data on the table. Remember that in the previous iteration, when I was fitting the model, I split it in half. So if I was to go with the model as is, I would be leaving half of my data on the table. I wouldn't be using it for future predictions. So what I'm going to do, I'm going to refit my model using everything. And to do that, I use exactly the same code, but I put validation split equal to 0. I want everything to be in the training data. This is how I want to get the best fit possible. And so here we see that we have a better than 0.92 for our accuracy, and we have a little bit of improvement, but that's deceptive. Do not trust this number. All right, this number is a training statistic. All right, what the algorithm is doing is trying to get the best fit that it can on the data. Now, remember, there's always a difference between your data and the population. We're using the data to approximate the population. Now, it's an approximation. It isn't, there is going to be a difference. This is an optimistic value right here. So really the best I could possibly hope for in performance is a 92% accuracy, and that is an optimistic number. Do not bet the farm on getting 92% accuracy off of this model. So honestly, I feel like it's going to be better than the previous fit, but not by much. It's more likely that I'm going to see something around 0.87, 0.88 for my accuracy. That is a more realistic number. All right, so now let's go ahead and take a look at the prediction. So now what I want to do, I want to run predictions. Now in real life, what would be happening is I would get new data coming in. I need to make a prediction on it. I need to make a classification based off of data that I have that I've never seen before. But I'm just going to go ahead and reuse the data just so that we can like proceed and explore things. And so here, I'm just dropping in the data. I'm dropping in the model into the predict function. Here, I'm going to go ahead and get some column names going so I know what each item is. And so here I can look at the actual output. And what I'm doing is I'm rounding off the first few rows of the prediction. Okay, so if I look here, we can see that for image number 5, it's 75% sure of itself that it's a t-shirt or a top. 16% is its mild likelihood of trousers, 6% is its mild likelihood of dress, and 4% is its mild likelihood of shirt. All right, so here it's not 100% sure. It could be either a t-shirt, a top. It could also be trousers, which is kind of different, right? It's kind of a surprising, split. But it could, it possibly could be a dress, possibly could be a shirt. We don't really know. We have to look. And so you'll notice that each row is a probability vector. So this is the modeled probability that an item belongs to a particular class. Okay. And so now what I can do, if I want to get which item does the model think each image is, what I'm going to do, I'm going to use the which.max function. So this is going to find the maximum value along each row. Now to get to go along each row, I have to use the apply function where I pass in the predicted values. My function is which.max. It's finding the location of the maximum value. It does not find the maximum value. It finds the location of the maximum value. And I'm saying go by rows. And then I'm subtracting 1 because positions start at 1. So the positions go from 1 to 10 here, but I want 0 to 9 to correspond with the original data sets. And so now I can get a confusion matrix to show me how things are going. So overall, the diagonal is where I want to see big numbers on the diagonal, big numbers on the diagonal. Okay, and so this is doing pretty well. I like what I see so far. Now there are some problems that for shirt, that's so that's one. So we had originally like 7,000 shirts in there, and when it is so here we're saying that the original item was a shirt, but 1,110 times the model said t-shirt or top. I mean, it's not a big difference, but that is a difference. So here, this is more than 1 out of 7. All right, so now I want to take a look. I want to dig into some problems with the model. I want to see if I can find, I want to get an impression on what's going on when a mistake is made, when we don't have very strong results. So what I decided to do was I want to look at just t-shirts and tops, dresses, and shirts. I ran this model a couple different times, and on one of the iterations, these 3 were the ones that had the biggest inaccuracies. So I went ahead and grabbed them. Okay, so I grabbed my predicted values of just these 3. I've got them in a data frame, and I'm tacking on the correct value. Now, I'm going to go ahead, I'm going to rescale my probabilities because remember that there are 10 categories. I have length 10 probability vectors. What I'm doing is I'm rescaling everything to have just the probability of those 3, and that so that they add up to 1 for each row. And now I'm doing a ternary plot just to get to see what's going on. All right, in the ternary plot, this corner here says the probability was perfectly 1 for t-shirt top. The probability here is perfectly 1 for the dress. The probability here is perfectly 1 for the shirt. So if the dot is in this corner, then it had probability of 1 for modeled value of shirt. If the dot is in this corner, it has a modeled probability of 1 for t-shirt top. If the dot is in this corner, it has a modeled probability of 1 for dress. Now, what goes on here along this edge? All right, well, you'll notice that here, things are going from dress to shirt. Along this edge, the probability of t-shirt top is 0, and these values are shifting from 1 to dress, 0 to shirt, to 0 for dress, 1 for shirt. And so along the way, here, this point right there on the graph is 50-50 dress and shirt. This point here is 50-50 t-shirt top and shirt. This point here is 50-50 t-shirt top and dress. Now, if I look at this, the exact perfect middle of all three of the points, this point is going to be where it models 1/3, 1/3, 1/3 for the probability vector. So this is saying that among the three, the model cannot figure out which one is it. So here, this is where we have the most confusion, and this is where we're the most confident, most confident, most confident. Now notice, every time I see a blue in the red region, or a blue in the green, a green in the red, a green in the blue, so on, every time I see a dot like outside of its neighborhood, that is a misclassification. So this gives me visually an impression of the inaccuracies that are happening. And so like this point is classified correctly, but you can see it's kind of getting away from where it should be. We want things to be solid in their corners. All right, well, that's all I've got for you. Take care and goodbye.